Here's the assessment on energy and bonding. You would have had one of these first two questions. They were asking you about the lattice energy required to separate some ions. And so we think about Coulomb's law. Again, it's an equation, but we're not going to solve for anything mathematically using Coulomb's law. Instead, we look at it qualitatively, where it helps us to gauge the degree of attraction between oppositely charged particles. That could be the protons and electrons of an atom, or it could be oppositely charged ions. And so Q1 and Q2 are the magnitude of the charge. That's the number one thing I look at. So if I have any ions that are higher charged, like a +2 versus a +1, or a -2 versus a -1, that's going to create a stronger attraction. And then in the denominator, we look at the distance between the ions. I want the distance between the ions to be small, which means then that they're small ions. So we kind of think about radius of the atoms or the ions now. If I've got smaller ions, they can pack more closely together. And so in the first option, of course, it was the magnesium and fluorine. Magnesium is +2, the fluorine -2. The calcium is also +2 and chlorine -2. But magnesium and fluorine are smaller. And the same thing kind of happens in the second option. We want one of the last two options. They've got the higher charges, but then magnesium and oxygen are smaller than calcium and sulfur. So those ions can pack more tightly together, creating a stronger attraction, and then it would take more energy to separate the ions. When we think about the formation of an ionic compound, there's a lot that has to happen. There's all these steps that occur in preparing the ions. Normally, lithium is a solid, and eventually I want to turn it into a positive ion. And so eventually I get to this ionization energy, right? Well, that's an endothermic change. And so if you start adding energy to the solid lithium, first it's going to go through a series of phase changes. And so in step one, we've got the lithium going from solid to gas, the energy of sublimation. Then once I've got it in the gas phase, if I continue to add energy, then I'll remove the electron. Both of those steps would be endothermic. Steps 1 and 2 require the addition of energy. Okay, now I've got my positive lithium ion, but I have to prepare the negative chlorine ion. Well, chlorine is existing as a diatomic gas. And so I want to separate those diatomic molecules so that they're individual chlorine atoms. Then I can add the electron and make individual chlorine ions. Well, that's bond energy, the energy required to break the bond. But bond energy is usually in units of kilojoules per mole. And so here, if I have half a mole in my balanced equation, then I'm going to need to divide that by half. The units that you would usually see are kilojoules per mole. And so the ratio in the balanced equation is a ratio of moles. So we're going to take half of that. But it's still endothermic. I have to add energy to break the bonds. Well, after steps 1, 2, and 3, then I finally start getting energy released. So once you've got the individual chlorine atoms and you gain the electron, I fill the outer shell, it's super stable, and it drops to a lower energy level. Electron affinity energy is exothermic. It's the energy released when the electron is gained. And then once I've got the two ions prepared, we transfer the electron, slap the positive and negative ions together in this beautiful crystal lattice. Then energy is again released. So electron affinity energy and lattice energy are exothermic, energy released. In general, the rule of thumb is that whenever you're trying to break things apart, you have to add energy. Whether that's going from solid to liquid to gas, if I'm separating the atoms, I'm separating them, I'm trying to break them apart from the original solid metal, that takes energy. If I want to remove the electron, that takes energy. But when you put things together, energy is released because you're probably putting things together in a way that makes them more stable. So when I put in the electron to fill the outer shell of chlorine, or when I put the ions together and they're positive and negative and they're very attracted to each other. Well, yeah, those last two steps are putting things together and then energy is released. Everybody had this one then. To get the overall energy change, you just add the energy from each individual step, but we just have to remember to take step 3 and divide by 2. Again, that bond energy is in units of kilojoules per mole, and so we only have half a mole. Awesome. So add them up, but watch out for the ratio in part 3. You would have had one of these two. They're kind of the same question, just asked oppositely. I drew the Lewis dot structures for each of the 3 carbon molecules that we're looking at comparing the bond energy for. And so once I draw the structures, now I kind of see the main difference. In the middle, the carbon-carbon bond changes from single bond to double bond to triple bond. So that probably would have helped if you didn't, to maybe sketch the dot structure. The first question wanted us to arrange the molecules from lowest carbon-carbon bond energy to highest. So then I'm going to go single bond up to the triple bond. And the second version of the question was just the opposite, going from highest bond energy to lowest. So then I would start with the triple and I would move down to the single. But again, sketching them probably would help, so I know what kind of bonds are present. Normally, I think about sketching the dot structures for a question like this too, where I'm calculating the energy change for reaction, and I've got this bonds broken minus bonds formed equation, which, by the way, is not in the packet. So Coulomb's law is not in the packet. We're not going to mathematically solve for Coulomb's law. We're just going to use it qualitatively, but I guarantee you're going to use it. This bonds broken minus bonds formed is, again, not an equation that's given in the packet. And I think it's because they don't want you to be on autopilot and just plug numbers in it. I think they want you to understand this process of making bonds and breaking bonds. That in a chemical reaction, the goal is to take your reactants and rearrange the atoms and make new products. In order to do that, you're going to have to break apart all of the original reactants so that I can then rearrange the atoms and make new bonds on the product side. Normally, I would draw the structure so I knew like if there's single bonds, double bonds, triple bonds, but here you kind of didn't have to. They just told you. So bonds broken refers to the reactants. I'm going to have to break that nitrogen-oxygen bond in the nitrogen monoxide. And then in the balanced equation, there's 2 moles of it. And this is kilojoules per mole. So I'm going to have to break 2 moles of nitrogen monoxide bonds and 1 mole of O2, oxygen-oxygen bonds. I add that all up and I get about 1,700 kilojoules. Energy needed, this is endothermic. I have to add the energy to break the bonds on the reactant side. Well, then technically I would do the same thing on the product side. Each NO2 molecule is going to have 2 bonds. Now, it's kind of a funky structure if you really try to draw it, and that you end up with it's called a radical, where you've got an oddball electron. Happens, not very often. And so we didn't even have to draw it. They just told us that that's kind of what we're looking for. What would be the bond energy of the nitrogen-oxygen bond in the NO2? The structure is a little different. Okay, so I just left that as my variable, but I did kind of think about the molecule, in that NO2 would have 2 nitrogen-oxygen bonds per molecule, and then I've got 2 molecules. So there will really be 4 nitrogen-oxygen bonds on the product side. They just left it as question mark in the chart, so I left it as question mark in my math. Obviously, you could put it as X or whatever you want to use as a variable. And so the key is that to understand this process, we have to know that bond energy is defined as an endothermic value. It's defined as energy I have to add to break a bond. But it's also the amount of energy released when the bond forms. And so when you're forming bonds, it's the same quantity, the same numerical value, but now it's exothermic because we're going to release the energy when we form the new bonds. So you could think of it as like the energy needed to break the bonds on the reactant side, plus the energy released when the new bonds form on the product side. And the overall energy change is the sum of those two processes. There's always the endothermic breaking of bonds and exothermic forming of bonds. Awesome. So then you do a little bit of algebra, and you should get about 500 kilojoules. And so when I solve for my question mark, which I guess I could take out this guy, and when you divide, you'll have like -4 and then -200. So I should get a positive bond energy. Energy needed to break the bonds, but it's the same as the energy released when I form the bonds. Then we have these energy graphs that kind of show us the relationship between bond energy and internuclear distance. And it's a careful science here when we make these covalent bonds, because if I bring the atoms too close to each other, there's going to be repulsion. And so if I have the two positive nuclei too close, they'll repel. If the electron clouds are too close, they'll repel. I want to find this perfect distance where the nucleus of one atom is attracted to the electron clouds of the neighboring atom. And so it's this fine line between attraction and repulsion. We want to maximize the attraction and minimize the repulsion. So when I look at the lowest point on these graphs, that's when the bond forms. Low energy is always most stable. So when I've released all this energy, I am most stable, and that's where the bond forms. And if you follow that point up, then you would get the internuclear distance, which is just the distance between the two nuclei. Sometimes we refer to it as bond length. Okay, so I've got these three molecules, HX, HY, HC, and they kind of tell me in the choices that, it's hydrogen, and then the XYZ is chlorine, bromine, and iodine. And so if I follow them up and I kind of understand what the units on this graph refer to, the longest internuclear distance should represent the largest atom. So if I have something like, oopsies, hydrogen's a little baby, so maybe this is hydrogen, and fluorine is still pretty, I guess they don't give me fluorine. I'll make a chlorine. So maybe here's like a hydrogen bonded to chlorine. But as I go from chlorine to bromine to iodine, iodine is a way bigger atom. So maybe here's my hydrogen again. Yikes! But I got something like this, hydrogen and iodine. Did I say iodine was the bigger atom? Hope I did. Iodine is much bigger than bromine or chlorine. It's got electrons distributed amongst way more energy levels. And so that's going to give me a longer internuclear distance. And it would make sense then that if the electrons are a little farther away from the nuclei, that if I were to follow it over, less energy was released when this bond forms, which also means less energy would be needed to break the hydrogen-iodine bond. Whereas the hydrogen and chlorine are a little bit smaller atoms, so they'll be closer to the nuclei and electrons of each individual atom. The attraction can be a little bit stronger. More energy released when the bond forms, more energy needed to break the bond. Cool. That was a good question. I like that one. I really, really like this one because, again, it's just the heart of this whole concept of making bonds and breaking bonds. When you look at the delta H, if you have a positive delta H, it just means that more energy was needed to break the bonds on the reactant side compared to the amount of energy produced when the new bonds formed on the product side, because this breaking bonds is endothermic. That's a positive delta H. Forming bonds is exothermic. That's a negative delta H, technically. And so I'm comparing these two values. So that, yeah, in the first option, It was a positive delta H. So you had to add more energy to break the bonds on the reactant side versus the amount of energy released when the new bonds formed on the product side. Of course, energy was still released when the new bonds formed. It was just less than the amount of energy initially I needed to add. The second one is exothermic. So of course we still had to break the hydrogen and oxygen bonds, but when I form the water molecules, I get more energy released. So now the sum of the bond enthalpies for the bonds and the reactants is less than the sum of the bond enthalpies of the bonds in the products. And again, enthalpy is just a fancy word for energy. But I really, really like this question too. It's just getting at the concept of making bonds and breaking bonds. Here we had 3 little energy graphs again, and they show nitrogen-nitrogen single bonds, double bonds, and triple bonds. That arrow should be pointing to the triple bond. The bond energy is greatest, and so it would take the most energy to break this bond. And if I follow it up, it's the shortest bond length. And as you go from single bonds to double bonds to triple bonds, the atoms do become closer together. In a nutshell, it's just that you're overlapping more orbitals and you're sharing more electrons. And that brings the 2 nitrogen atoms closer to each other. So they'll have a shorter bond length and they'll release more energy when the bond forms versus a single or a double. Then again, more energy is needed to break the triple bond. And then finally, we hit the free response. Everybody had the same first part to the free response. You had a reaction with fluorine and nitrogen, and we wanted to calculate the energy change for the synthesis of N2F4. And so they gave you all kinds of different bond energies. I mean, I've got that nitrogen single bond, double bond, triple bond, and you really don't know which to use until you sketch them. So I think sometimes that's maybe where we went a little funky on this one, is that we used the wrong nitrogen bond energy, that it really ends up just being the triple bond in the N2 molecule, but in the N2F4, it's all singles. So I did draw it just to know what kind of bonds I'm dealing with. Then we go bonds broken minus bonds formed. And so I added them all up, and you should really be left with just a +1. It's kind of random. And it's a really similar bond energy between the products and the reactants. But in the end, you would have needed to add about 1 extra kilojoule to break the bonds on the reactants in comparison to the amount of energy released when the bonds on the product side formed. Since it is positive, it's endothermic overall. And again, your data kind of proves it, and your calculations kind of prove it, that the bond energy of the reactants was greater. Overall, still a positive delta H. It was endothermic. Barely, but it was. All right, then there were 2 different versions of this graph, so you could have had one of the 2. A student attempts to draw a potential energy graph for diatomic fluorine and diatomic nitrogen. Explain what is inaccurate about the student's graph. Well, right there, they're telling you that there's something wrong with the graph. On a few cases, people were like, looks good to me. Like, looks great. They drew some awesome graphs. No, they didn't. They're telling us there is something inaccurate about the graph. Okay, so here too, they kind of show me that the nitrogen is a triple bond, and the fluorine is a single. So I'm not going to get that wrong. Okay, well, here might be the problem then. If I'm looking at the bond energy, like the low point here, and if I follow it across, it tells me the amount of energy released, because these are negative numbers down here. That's technically energy released when the bond forms. But if I make it a positive, it's the amount of energy I need to break the bond. That triple bond should be stronger. And so more energy should be needed to break a triple bond versus a single bond. So the trough should just be lower for the N2 molecule, not the F2 molecule. And in reality, You could talk about the bond length a little bit, but the bond length is probably okay too, because I mean, again, a triple bond should be a shorter bond length than a single. And I get that nitrogen atoms are technically a little bit bigger than fluorine, but they're really close to each other on the periodic table. And so, yeah, fluorine has an extra 2 protons and electrons, and the attraction is a little bit stronger, but just an atom of oxygen and an atom of fluorine are in the ballpark as far as radius goes. But now when I bond them, that triple bond really should give me a shorter bond length. That's a stronger bond. And then part D, which ionic solid would have the higher melting point? So again, if I'm melting, I'm separating the ions. So the higher melting point means I need more energy to separate the ions. So there's a stronger attraction. Here you've got everything with a +1 or -1 charge, but the sodium would be smaller than the potassium, and they can kind of tuck and pack more closely together, and that would create the stronger attraction, which would then leave us with a higher melting point. Very good, I like that stuff. Here was the other version of the graph that you could have seen. It was real similar. It was still the fluorine and the nitrogen. This time they do show the bond energy properly, and that, yeah, the bond energy of the triple bond should be higher than that of a single bond. But now my problem comes with the internuclear distance. That if I follow these up, whoa, that's kind of straight. If I follow them up, that nitrogen triple bond should have a shorter internuclear distance, or a shorter bond length. And again, there were a handful of people that were like, looks good to me. But they tell us to explain what is inaccurate about this graph. So then you know right there's something wrong. Well, it's either going to be wrong with the internuclear distance, or the bond length, or it's wrong with the energy. And the energy is fine, because yep, now more energy should be released when the triple forms, more energy needed to break it. So then the error has to be with the internuclear distance. And then I had sodium fluoride versus magnesium fluoride for my ionics. The higher melting point should go to the magnesium fluoride, because magnesium would have a higher charge than sodium. The attractive force would be stronger. And again, I would then need more energy to melt the solid and separate the ions.